Hello all and welcome back. So in this video, let us continue our discussion and now let's see another way through which we can implement our graph. Till now we have seen a edge list and the adjacency list as ways of implementation of our graph and understood the pros and cons of both. Now the last one is the adjacency matrix, and the idea behind adjacency matrix is something like this. Let's say we have a graph again, something where we have four nodes. Let us take it 3, will be easier to draw. Let's say we have some information like this. They are all undirected graph. This is A, this is B, this is C. What I do in adjacency matrix is I create a n square matrix, okay, where n is the number of nodes. Something like this: A, B, C, A, B, and C. So now if you will see, if A is connected to B, I think yes, that means B is also connected to A. Is A connected to C? No. So C no, also not connected to A. Now is B connected to C? Yes. And rest all will be 0. Like there is no loop or anything. But yeah. This is the kind of overall matrix which we have created, right? So it's a n square matrix where we can very easily find out if two nodes have an edge between them or not. I have just taken one. It can be weighted as well. I hope all of you agree on that. Plus again, it can be unidirected and sorry, in a directed graph. If you just make for let's say A to C or A to B, we are just making it one for A to B and not for B to A. So this overall implementation, the maximum benefit is that it is very easy to understand, to visualize. Okay. It is also the reason you will see it in many places in competitive coding, in lead code exercises. You will see this kind of adjacency matrix getting used. So the benefit, let me write it down. Easy to implement, quick, right? So if I want to find out if you are following, let's say, Cristiano Ronaldo, I will just take you on one axis, Cristiano Ronaldo on other axis, and I will find out if it is one, then it's fine. Very quick, right? All the information is stored. So it's very quick over one in a real sense because we just have to see that where these things are kept. Now, next thing where the problem is that space heavy. Now, in our adjacency list or in our edge list, we were just adding anything if the edges were there. But here, even if the graph no edges are there, we will have to still maintain this ON square matrix where n is number of nodes. So you can think that how bad overall it is in terms of space. Though because of ease of implementation, we normally try to use this only. The next thing is not recommended for sparse graph. Okay, so sparse graph is a kind of a graph where we have very less number of edges. Okay, so for that it is not recommended, and we can see the same as well. It will have lots of zeros. Okay, but again, as I said, normally we have a graph where edges are there, and for ease of use overall, ease of implementation, we try to use adjacency matrix as well. Okay, so let us see that. I hope you get both the positives and the negatives. Let us try to now implement this, everyone. So let us go back here. This was what I was telling. So here from E to A, all that I don't have to store. But in my adjacency matrix, we'll have to store each and everything. Great. So class graph adjacency matrix. Now a constructor. Here along with constructor, this time you will have to give me number of vertices as well, because I have to create this matrix from the very starting, right? So self dot num vertices equals num vertices. Now I can make a self dot vertices as well, which I am taking none initially. Okay, so none into number of vertices, because there can be these many number of vertices, right? Next is self dot adjacency matrix, which is going to be equal to, see, first we will have a list, a 1D list of 0 into num vertices. Then I can say for row in range num vertices. Just to show you how this works, let us copy this. Let us open the test one which we created. So yeah, pay attention everyone. If I'm, let's say, creating something like this, adjacency matrix, let's say we have 5 vertices. Okay. So this overall first creates a list of zeros. I think this all of you will be aware. So I'm getting a single list where everything is 0. To make it into a 2D list where I want that there should be 5 more such lists, I am just using list comprehension and running a loop for row in range 5. So if I just print out this adjacency matrix instead, see, let me just collapse it so that it is list. Yeah, great. Now see, in a way we have created this adjacency matrix. We will be maintaining the index. Using that index, again, we can just say that, okay, if it is there or not, like let's say for, if the first node is A, then this row will become A. This one and this one. This column and this row will become for A. Then B, something like this. Okay. Let me close this. We should be now fine. Okay, this is the test one, ADJ matrix. And let me zoom it out as well. Great. So the constructor is done, I think, everyone. You should all be clear that what exactly it is. Now def add vertex self. I'm asking index as well this time. Okay. So if index is greater than equal 0 and index less than self dot num vertices, then only I should be adding it. I hope you're able to understand this as well. One thing more, we are doing a very simplified overall implementation, but believe me, this will also, you will not be able to find it. People must have used a single, maybe just an adjacency matrix. They must have not defined vertices. In many implementation you can find that, but again the basic idea is same. This is way better than any of the implementation. Plus in graph, the problem again is you will not find a lot of resources, because again everyone gets tired till they come to graph, right? So I made sure that each and everything I'm able to explain you properly. But if you see some other kind of implementation, don't get scared. This is exactly the same. Rather, you will find difficult implementation than this only. You will not find this easy of an implementation. Okay. But I hope you are getting the concept right. That, okay, why are we doing it in different ways? Why coding each and every one? What is the benefit, pros and cons of each and every one of them? Okay. Great. So self dot vertices. And let's say in the index, 1 minute, let me just think, do we need this kind of a thing? None is there. Okay, if I want to just name it, if let's say, yeah, so there can be a name or label as well. Okay, let us use this label instead, and we can have this label here. Now the reason is that if I want to store A, B, these kind of a label, then we have to use this kind of a structure. Okay, so what I have done, at this index, I have said that, okay, this is the label. Great. Else, we can just print index out of bounds. Okay, so you will complete this out, should be fine. Then next is add edge. Again, we have to add edge between a source and a destination again, and weight is 1. Pretty easy. If we have to this time check with respect to number of vertices, right? So if my self dot source, yeah, so we have to just check for this same condition. But what I'm going to do, pay attention everyone, I'm going to check it all together. So if you remember, they can be clubbed together, right? These conditions, these relational operators can be clubbed together. So that is what I've used. And 0 destination and self dot num vertices. So I will be telling in terms of the indexes that, okay, where I want the overall edge to be, right? If I will say 0 and 1, we will take 0 from here and 1 and make this and this one. Okay. If this is the case, then it's very easy. Self dot adjacency matrix source destination, and we say weight here. Again, because weight is 1, we are saying that okay, store weight in that particular position, and I can just copy it and make it destination and source. So I will repeat everyone till now what we have done. We have made and stored what are the number of vertices. Just to make sure that we can support A, B, C, these kind of a names instead of 0, 1, 2, we have just stored the index. That okay, at which index you want which vertex. Okay, so let's say if you say at 0 I want A, if at 1 I want B, then you can just use this. Next is adjacency matrix. Initially only we have created that by asking the number of vertices. Okay. Then we are adding a vertex. In this vertex, we are using this label because we are trying, we have an idea that what is a labeled graph. So we are able to add a vertex. Then we are just adding an edge. Edge again is very easy. If you know the overall indexes, you can just go there and put 1 here. If you want it to be weight, then we can put some other value instead of weight. Okay. So straightforward implementation, nothing major, just that again, we are using just many things. So we have a list here, a list here, a list of list here. Okay. But till now I think we have understood each and everything in this particular course a lot in depth, right? So it should not be difficult. If you are finding difficulty, I would just suggest you one thing, go back to the OOPS module, see the videos, try to do the OOPS question, try to see how I helped you implement the list module as well. There's a video of, I think, close to an hour, 2 videos and a question as well. Try to implement that. Come back, try to implement the adjacency list, the edge list, and then come back to here and you will be able to understand each and everything. It is not again difficult, but I want to make sure that each and every one of you are able to understand this. Okay. So undirected graph. Great. Now the next one is display. So display, I just need self. I don't need anything else here. What we have to do here? So for vertex and label in self dot v, it's a list, right? And here I am saying that okay, this is at this index, I want this label. Okay, so let us see how exactly will we be doing this. It will not be, actually it will be a label. Okay, so there is a function which I will be using here, everyone. There's an enumerate function which you must have studied. So to show you how that is, let's say if I have a list, something like L1 equals A and B. Okay. For I comma j in L1 enumerate, okay, L1, and if I just print this I and j to you, so pay attention what's going to happen. See, I'm getting 0 and A, I'm getting 1 and B. So it gives me the index along with the index, it just gives me the label as well, the value. So at A I have 0, at B I have 1. So just using that to make sure that I can show you that vertex and label. If we have the label, because see, we will have the overall, if I make it none, pay attention everyone. If I make it none, and if I print this now, I can just check if it is not none. If it is not none means that the overall index, overall node was added there, right? Pay attention. In the starting, I don't have any node. Then I add some nodes or vertices. If it is empty, if it is none at any particular index, then I can say that, hey, no node was added there. So if it is not none, then I can say that a node was added. For example, print f vertex index. I can have the index. You can use index here instead of vertex. And in label. Okay, great. Adjacency matrix is a lot easy. For row in self dot adjacency matrix, we can just print out the row. Great. And this completes our graph. Overall, we're using adjacency matrix as well. What we can do now to check it out? graph equals graph adjacency matrix. Let's say I'm making 3 nodes again. We did 3 here, right? So let us try to make this one only. There is a A to B and B to C. These are the edges, right? So graph dot add vertex. At 0, let us add A. Then at 1 and 2, let us add B and C. Just to check, let us add at 3, let us add D, E, F. Or let us add D. It should not get added. We should get an error. Graph dot add edge. Edge I am adding between A and B. Okay. So it will be from 0 to 1. And I'm adding edge from 1 to 2. So from B to C. From B to C. So this is 0. This is 1. This is 2. 0 to 1, an edge is there. 1 to 2, an edge is there. Which means I am just adding edge like this. Great. And we can do graph dot display. Cool. I think this should be fine. You can just take a minute here, pause it, and try to draw the overall graph which will get made. Okay. So let us now run this. Okay. Where we made the error has no attribute V. Okay. Yeah, I think it is vertices, not V. And not enough values to unpack in line 20. Index and label. My bad. We have not used enumerate. We have to use enumerate here. So we get 2 values. Great. So pay attention, everyone. It is showing this index out of bounds. Where is this error? When we try to add it here. 0. Yeah. So see, we tried adding. We didn't see any error here. For this D, we saw an error. Index out of bounds. Then this display first showed us that, okay, where the index is present and what is the label. So we are able to see this. Let us try to draw our overall graph using this information. See 0, 0, 1, 2, 0, 1, 2. We have 3 nodes. Let's say this node is 0, this is 1, this is 2. They have a label attached to them, A, B, C. So this is giving me the information about label this time. Then from 0 to 0, nothing is there. 0 to 1, there is a edge. And 1 to 0, also there is an edge, that is fine. Then 2 to 1 also I have an edge. This is also an edge which we have to draw. So let us see if this was the same graph we started with. Seems like, see, A, B, C and A, B, C. So we are able to get each and every information in a very good way. If someone is able to see the graph like this, he should be having the full idea that, okay, this is what the graph looks like. Okay. Great, everyone. I hope this was helpful. The way we have done all these different approaches are very important to understand. Now let us meet in the next video and see different traversals which we can do on our graph. Okay. Just make sure that you are practicing this once at your end as well. And all of you will be able to pretty nicely write the same because we have just followed a simple OOPS concept in them. So let's meet in the next video.